You're looking at the opening screen from HEC-RAS. I have loaded HEC-RAS NC-190, and it's the Riffle pool final design. Let's first take a look at the cross sections. Now notice in my graphical representation, I've made a crude attempt to show the meander of the stream. And now I have my 10 cross sections. And we'll look at the cross section data. So you'll notice this I copied in from the spreadsheet. Since it's the most downstream section, these are 0. In all of my riffle sections, the left and right bank are going to be 200 and 233. Here's the Manning's N, calculated from the riffle design, and here are the overbank values. Now notice here we'll talk about, I did a simulation, and we'll discuss that very shortly. Here's the next one, bringing the information in directly from the spreadsheet. And then here's the 28 feet to the distance to the downstream section. Now when we go to section 30, we put in the first pool section. And you can see the information is the same, with the exception that the pool is 56.1 feet wide at its top. So the top of the right bank station will now be 256.1. And another pool section. Section 50, another riffle. 60, another riffle cross section. 70, the pool. 80, the pool. 90, the riffle. And the last section being 100, the riffle. Now, the elevation at section 90 must match the water surface elevation at section 10. So let's take a look at the flow data. Looking at the steady flow data and boundary conditions, the flow was 300 cubic feet per second for bank full. Now if I look at the reach boundary conditions, I have a known water surface, which is 99.58. So the lowest part of the channel was 97. So 99.58 minus 97 is 2.58 feet. Now if we look at the profile summary table, we look at, this is 2.58, and if we go up to section 90, we have the channel bottom is 98.68 and the water surface is 101.25. If you take 101.25 minus 98.68, that gives you 2.57 feet. So you can see I have the same depth of water at section 10 as I do at section 90. Notice it's subcritical flow throughout the entire reach, and it gives you the range of the velocities. Now let's take a look if I were actually going to run a steady state simulation. And if you look at the depths of the flow, I tried several of them before I actually arrived at the solution of 2.58. So the elevations that I chose did not give me the same value of the depth of the water at section 90. Now let's take a look at the water surface profile. So you can see It's not a real uniform velocity head, but considering the dramatic depth changes, it's a fairly uniform velocity head through this section. So you notice I'm simulating 2 meander wavelengths plus a little bit more coming through here. Now excuse me, I am simulating 1 meander wavelength because 1 meander wavelength consists of 2 riffles, 2 runs, 2 pools, and 2 glides. Now if we take a look at the cross sections, and we'll start at section 10. Now you notice the selection of my riffle. When I picked the geometry, I upsized it just a little bit, rounded things off to make the dimensions even. Well, by doing that, at my riffle, I did not achieve bank full flow. I am down below the bank. So basically I have created a little bit of an entrenchment that I don't want. I want the water to have access to the floodplain at flows which are above the bank full level. So you can see this, I would go back and make my riffle smaller. My cross section for my riffle should be reduced in size. And as you can see, the same thing. When we get to the pool, you can see I'm doing very well. My bank full flow is right at the top where it should be. Working my way, I have again almost right at the top for the pool. And this pattern repeats itself up the entire reach. So once again, I would go back and redesign my riffle to make it smaller. So in this file, what we have looked at is the insertion of the cross sections copied directly from the spreadsheet. And then we have looked at how you must iterate on the downstream boundary condition to come up with the depth at section 10 that matches the depth at section 90. We examined the water surface profile to see if it looks realistic for the simulation of a riffle, run, pool, glide sequence. We examined the profile summary table to make sure that the flow is entirely subcritical, and here we can get the velocities, which we would look, for example, the velocity through the riffle, or the maximum, would be described as, would be given as 4.83 feet per second. We would then go back and look at the guidelines to see if this is what would be recommended for a C4 channel. So what you're going to do is you're going to design an E4 channel, and you're going to come up with a HEC-RAS model similar to what I have done here for the C4 channel.